episode of our Prague seminar of mathematical physics. And it's my great pleasure I can introduce Simon Jonsson from the University of Hertfordshire in the United Kingdom. Simon was so grateful to bring amongst us a very nice topic, I guess, with a long title and maybe not even that. So he's gonna talk about twisted canonical supermultiplets and their resolutions as open-closed homotopy algebras. So Simon, thank you very much for coming, and if everything works properly, the floor is yours.
Okay, very good. Thank you very much for inviting me. This is actually my first invited talk, so I'm excited but also a bit nervous. So, and I hope I will do somewhat well. Feedback is appreciated. Yeah, I'm gonna be talking a little bit about my my most recent paper, basically the same title as my talk. Let's just go through the outline. So I'm gonna when I was preparing for the talk, I got the instruction that I should make it like try to make it pedagogical and somewhat basic, which is appreciated by everyone, I hope. But if you find that it's too slow, then let me know, and I will speed things up, and then we can have interesting discussion at the end. But I will first just go through a little bit of an overview of how I think and how many people think about like physics and math in the in later years. In particular, how the field of homotopy algebra can be used to understand some physical phenomena. And then I will go through somewhat of a broad overview of like homotopical algebra and some interesting structures which I work with, which are relevant for the paper that I wrote. And then I will go through briefly the framework in which I'm working when I work with supersymmetry, which is the pure spin of superfield formalism, which is a universal framework for constructing off-shelled supersymmetric multiplets. And then lastly, I will go on to more or less the new results of the paper, where we can see that some supersymmetric multiplets can be equipped with the structure of what's called an open-closed homotopy algebra. And in particular, we will look at some a span of those. So it's a triple of physically equivalent supersymmetric multiplets. So let's just dive straight into the general philosophy of how I try to think about things. So in physics, we're often like interested in the space of solutions to the equations of motion of some field theory. And there might also be like gauge symmetries that we have to mod out to find like the real bare physical quantities. And these spaces are often like quite awkward to work with, and there are a lot of constraints and stuff that are present. And so one would like to have more to find more simple models for working with these. And this is basically what drove the development of what's called the Batalin-Vilkovisky formalism. This formalism also then bridged the gap between the the physical field of like quantum field theory and string theory, and then what's called homotopical algebra. And in very broad brushstrokes, what like the idea is with this formalism and this mathematical framework is that these awkward spaces, quotient spaces, for example, that you try to investigate. What we try to do is we want to express these, or in a more mathematical wording, resolve them with simpler ones, so as to still keep the physical physical quantities, but making computations a bit easier. And diving more towards the motivation about supersymmetry and why I'm interested in particular the pure spin of superfield formalism is in supersymmetry. It is sometimes challenging to find representations of the supersymmetry algebra which is valid off shell. So what that means is that if you sometimes say that the supersymmetry algebra is only represented on shell, that is after imposing the equations of motion. And this again was a major driving force in the development of the BB formalism. And like relatedly, like actually constructing these supersymmetric theories or even supersymmetric multiplets, for example, using standard techniques of like superspace, can be quite tedious at times. I remember some class from university when I had to set up like the Bianchi identities for some gauges, a gauge theory in 10-dimensional superspace, and then solve put some constraints and then solve the Bianchi identities to like find a multiplet, and that's quite tedious. And so what we would like to do is find like systematic and uniform methods for constructing these supersymmetric models. And that's basically what the pure spin or superfield formalism does. In addition, it also provides a quite natural setting for what's called supersymmetric twisting, which is also have gained some popularity in later years, and like the first paper on this is I think by Witten back in like the 70s. So just a brief summary of the talk again. So this is based on my most recent paper, but it's in essence a continuation of a previous paper I wrote back in 2023 together with Martin Cederwall, Jakob Palmqvist, and Ingmar Saberi. And there we also work with the pure spin of superfield formalism, and in particular, we work with something called the canonical multiplet, which we'll come to later. But this is uniquely defined by each supersymmetry algebra. And interestingly, these canonical multiplets are not just multiplets; they also carry a commutative algebra structure. So they have a multiplication. And in fact, in some examples, this multiplicative structure is strongly related to the interactions of the underlying field theory. Examples includes like 10-dimensional super Yang-Mills and 11-dimensional supergravity. And so studying these multiplets, in particular their algebraic structures, can provide interesting insights into to construct supersymmetric field theories. But importantly, for this paper, we have these type of multiplets, which are then modules over the supersymmetry algebra, but they're also algebras themselves. And so it's interesting to ask about the compatibility with these two structures. And that's basically what, how and why the open closed homotopy algebra are relevant. And as I said, then supersymmetric twisting is where you pick out some square zero supercharge, and you're basically looking at like a protected sector of your supermultiplet, i.e., looking at the Q cohomology. And so it's natural to then I ask how twisting works with these multiplets, which are also algebras. Just a quick interlude about like notation and things we're gonna gloss over a little bit just to make this talk a bit more enduring, hopefully. So we're gonna ignore potential signs and multiplicative factors. We will be working with what's called graded vector spaces a lot, but we're not really gonna go into the nitty-gritty of which thing has what grade and stuff like that. So we will just talk about again, broad brushstrokes, and then to hopefully make things a bit more easily read, we will mostly write out maps diagrammatically, and these diagrams are then written in a top to bottom fashion. So we might have some tree where the leaves are the inputs of our function, and then they go down to some output, and then as you see on the slide here, I'll just depict the identity map as just straight lines or solid lines. Unary maps, things that take one input and produce one output, is usually denoted by a bullet. And then if we have maps of different vector spaces that goes together and produces whatever is for example depicted as you can see here, where you have different shaped lines for different vector spaces. Right. So let's go on to the first like actual interesting thing about the talk, which is homotopy algebra. So when working in the BV formalism and homotopy algebra in general, the bare or the most fundamental mathematical object that we work with is something called a cochain complex, or a differential graded, well, or more often a differential graded vector space. And that's in principle just a sequence of vector spaces together with maps between them, such that the image of each map lies in the kernel of each subsequent map. So I have this nice pretty diagram here where we see that the image gets mapped to 0. Given a cochain complex, you can define something called the cohomology, which is then basically just the quotient space of the kernel module of the image. And the idea, going back to the general philosophy, is that the cochain complex is this bigger, easier thing to work with, and the cohomology itself is then the bare physical quantities, such as the space of solutions to the equations of motion modulo gauge equivalences, say. But very good. However, the cohomology and the cochain complex itself are, of course, not isomorphic, because the one is just a subquotient of the other. But we would still like to find a means to say that these are equivalent in some sense, that the cochain complex encodes the same information as the cohomology does. And this is what is called sometimes to work up to homotopy. So if you recall your undergraduate studies, an isomorphism of vector spaces is basically just a pair of maps such that the composition in any direction is the identity. In the setting of homotopy algebra and cochain complexes, you relax this. So in addition to this pairs of map between the spaces, you only assume that their composition is the identity up to homotopy, and then where the homotopies are then these mapped H's here on the slides. And from a physical perspective, then the idea of these homotopy equivalences, or in other words, also called quasi-isomorphisms, is that they encode physical equivalences of theories. So, for example, if you start with some big thing, say, and you go to a smaller cochain complex, corresponds basically to like having a lot of fields and then integrating out some fields to move to a smaller model for your theory. Okay, very good. So now we have these underlying vector spaces that we're trying to work with. What kind of algebraic structures can we then put on these structures? On these vector spaces. Well, the first obvious thing is to talk about Lie algebras. So just to recall that a Lie algebra is just a vector space together with a skew-symmetric bilinear map such that the Jacobi identity is satisfied. And keeping with this homotopy business, we can define what's called an L-infinity algebra, or a homotopy Lie algebra, where you, instead of just an ordinary vector space, you have a graded vector space. And then you have a family of skew-symmetric or graded skew-symmetric multilinear maps, like mu1, mu2, mu3, and so on, which satisfy a tower of Jacobi-like identities. So, for example, mu1 here acts as a differential. So what equation 4 says is just that the mu1 squares to 0. What equation 5 says is that the mu1 is a derivation with respect to the binary bracket mu2. What equation 6 says is that the Jacobi identity for mu2, that is the would-be ordinary bracket, is only holds up to this weird sum here, which you don't have to remember at all, but is basically also a homotopy. So you're relaxing the constraints that you put on a Lie algebra. You might think that this huge tower of multilinear maps and these weird tower of Jacobi-like identities is well, it's a lot of information. So you can ask the question as is it possible to like boil this down to a more compact notation? And in fact, you can. This is sometimes referred to as like crucial duality between L-infinity algebras and commutative algebras. So there's a one-to-one correspondence between L-infinity algebra structures on a vector space G and square 0 derivations on the symmetric algebra on what's called the shifted dual of G. Shifted here is with respect to the degrees, but we kind of forget about that. And the idea then is that the differential, which can be written as in equation 8 here, the coefficients of these, if you choose a basis, corresponds to exactly the structure constants mu(n) of from this slide. So, for example, you take in two things, that would be the second term here in this sum. And I forgot to write this on the slide, but the fact that d is then square 0, so that d squared equals to 0, easily enough, is equivalent to this tower of Jacobi-like identities here. And so you can encode this whole structure of an L-infinity algebra just by defining a derivation on the symmetric algebra. Very good. And let's quickly go over associative algebras, which have basically the same type of idea, but I'll just put it in here because, well, for completeness. So you, for an ordinary algebra, you just have some binary product such that it is associative. And then likewise with as with L-infinity algebra, so you can define something called an A-infinity algebra, where again you have a tower of multilinear maps. So you have a theory map and higher, and these satisfy now a tower of like associativity like identities. There is a similar notion of this Koszul duality business that I mentioned just now, but it's not of relevance to us. But just so that you know that you can encode these structures and these relations in a similar fashion as for as for the slide here. Now we have L-infinity algebras and A-infinity algebras. Let's go on to open-closed homotopy algebras. So a bit of background. So say we all know what a representation of a Lie algebra on some vector space is. That's basically just a Lie algebra homomorphism between G and the Lie algebra of endomorphisms of your vector space, say A. Now, say you have that, but you have in fact also that the underlying vector space that G acts on is an algebra. Then a suitable notion for A to be an algebra over G is to say that the morphism, the action morphism, factors through the space of derivation of the product on A. I see I have made a typo here, so in 15, of course, M is supposed to be A. And this is should be quite natural to think. Like the standard example would be, for example, the space of functions is a module of the for example, if you take some manifold, you have the space of functions on it, and it's acted upon by the Lie algebra vector fields. But in particular, the Lie algebra vector fields acts with through derivations with respect to the pointwise product on the space of functions on your space. So that's like one example to have in mind. So what happens then if if the Lie algebra that acts is an L-infinity algebra, and the vector space which it acts on is in fact an A-infinity algebra? How do we cope with all these higher products, and how do they interact with each other? So this was basically then generalized by Kajura and Stashev, and this was motivated by the open-closed string field theory of Sweeback. I have to apologize in advance if there are questions about the string field theory part of this. I've just dealt with this algebraic notion of it. So basically what an open-closed homotopy algebra is is you take a graded vector space which has a splitting into, well, keeping in with the notation by Cajora and Starship, you have a vector space which is like G closed and a vector space which is G open, and a space of maps and a family of now partially skewed symmetric. So it's skewed symmetric when the input is from GC and it's non-symmetric when the input is O. And these basically satisfy some quadratic relations. In particular, that these NPQs for Q equal to 0. So when you only have inputs from G closed, ends up in G closed, and defines an L infinity algebra on G closed. Similarly, when the only input is in sorry, this is also a typo. This is supposed to be G open. It also ends up in G open, and it defines an infinite algebra structure on G open. And then you have a bunch of other maps which takes in several things from G closed and some things from G open, and then ends up in G open. And these defines what's called an infinity representation of the L infinity algebra G closed on the underlying vector space G open. And then you have this type of compatibility relations between this action and the product on G open, and this is termed derivations of the homotopy. We don't really care so much about exactly what they look like, because they're just awful formulas that you just write down once and then you don't have to remember them. They're just there. But this in principle encodes the homotopy version of having a Lie algebra acting on an associative algebra through derivations. Right. Finally, let's just briefly discuss the notions of then morphisms of homotopy algebras. They work in principle the same way for like L infinity, A infinity, or open closed. So as recall, the a morphism of Lie algebras is just a linear map from the first to the second, where you can like multiply the first things in G first and then map it, or map each individual thing into H. Yes, map each individual thing into H and then multiply them there, and that should be the same. But here, as we're all relaxing all the constraints, we have now a family of maps which takes some inputs in G and gives out one input in H. And so, for example, 19 here is the analog of the thing I just told you about. So you can first multiply two things, that gives you something in G, and then map it over to H. Or you can map each individual thing over to H, and then multiply them. And so in an ordinary setting, that this should be 0. Recall that we don't care about signs. But now in this setting, it is only 0 up to homotopy. And we say that two homotopy algebras are quasi-isomorphic if phi 1 here is a quasi-isomorphism of the underlying chain complexes. So if you recall in the beginning where we defined a quasi-isomorphism. Actually, I didn't mention that. So a quasi-isomorphism between two chain complexes is a map of the chain complexes such that it induces an isomorphism on the cohomology. And this is what I should have mentioned at the beginning, where if two things that might look different have the same cohomology and the cohomology itself is the bare physical thing, and so these two different looking things with the same cohomology should encode the same type of physics. Very good. So how do we, if we have some big thing, some big cochain complex, and we would like to, in principle, well, there is a way to, given some algebraic structures on one thing, transfer this algebraic structure to another thing, and this is called homotopy transfer. And this is I will come to this on the next slide, but this is in principle high-tech version of what's called homological perturbation theory. So let's just go through this slowly. If I have two vector spaces or graded vector spaces, and if you recall at the beginning, I had this notion of a homotopy equivalence where we had a pair of maps and then these looped h's here around. So if we assume that one of these are 0, we get what's called deformation retract. And if we deform the differential here dm such that by some endomorphism, such that the resulting thing is still a differential on m, then assuming some finiteness conditions are satisfied, you can transfer this perturbation along the retract here, such that we obtain a new deformation retract with this new perturbation. And this is useful in this business, because sometimes you might have that, as we shall see, that you have some scary looking differential on some vector space, but you have one specific part of it which in itself is a differential, and perhaps that the cohomology of that differential is easily computable. So then what you can do is you can start by defining then a deformation retract from the original vector space with this only the first part of the differential down to the cohomology of that differential, and then add the rest basically, and that gives you that allows you to define then a differential on the somewhat smaller thing, I realize when I'm saying this, it might not be very clear why it would be useful, but it sometimes simplifies a lot of the computation that you do here, and we will see some examples later on. Let's go on to the homological perturbation lemma's high-tech sister under the name of homotopy transfer. So on the previous slide, we only transferred like parts of a differential, but you can in fact transfer entire algebraic structures if they are sufficiently nice. So say I have a deformation tract of some graded vector spaces, and assume as well that the G here on the left is some homotopy algebra, say an L-definity algebra or open closed homotopy algebra or whatever. Then via this retract, you can transfer the algebraic structure on G to an algebraic structure on H, which will be equivalent up to homotopy. So you will obtain two things which are quasi-isomorphic. And this is done by a procedure of like gluing trees together, for example. So the ternary product on H would, for example, look like 23 here. But what do you do? Well, you start with things in H, you map it into G, you multiply it there, and then you map it back. But then in order for you to have the right to have them satisfy the Jacobi identities and stuff like that, you need to do some extra things, which are gluing parts together with H along the edges. This is also very important in the BB formalism and by audience who work a lot with this, where this type of homotopy transfer for some corresponds to basically computing the tree level Feynman expansion of your scattering amplitudes. You can perhaps see that this sum here 23 is very similar to pictorially quite similar to a Feynman expansion. Okay, hope you are still awake. Let's go on to the pure spinor superfield formalism. So why I started talking about the homotopy algebras and stuff is that the pure spinor superfield formalism makes heavy use of homotopy transfer, the homological perturbation lemma, and homotopy algebra in general. I saw that, I think perhaps a year ago you had a nice talk by Simone Noja, who went through the pure spinor superfield formalism in more detail than what I will do now. So if you want to listen to a talk there, that's the one to listen to. So as I've said before, the pure spinor superfield formalism is a universal framework for constructing supersymmetric multiplets, where the action of supersymmetry is realized even off shell. This has been developed by the works of many. I think one of the first one was Nilsson back in the, I think, 80s, and then some famous names have developed it, and in later years, particular by works of Saberi, Eager, Honor, Williams, and Elliott, they worked out a nice mathematical like algorithm for how these pure spinor constructions work. So I will go through it in quite quickly, but let's just first agree upon what we mean by supersymmetry algebra. And they will in general take this form 24 here, where we have some semi-direct product of some Lie algebra G on some super Lie algebra T, and which is the well, the direct sum of two direct sum of two vector spaces. So T1 here represents your supersymmetries. T2 here are basically your ordinary spacetime translations, and G0 are more or less the Lorentz symmetries and R symmetries, if you want to think of it from a physics perspective. So P here is some super Poincaré algebra. So all examples of in any dimension and with any amount of supersymmetry fits under this definition. We in this talk we don't really care about the specific spin representations and stuff like that. We just take the algebra to be of this form, and so then 25 here is the ordinary supersymmetry algebra equation that you might have seen, where you take the bracket of two supersymmetries is a translation, and then this gamma alpha beta here is when working with like spin representation, this is some intertweener between the spin representations and the fundamental representation. And where does pure spinor come in? Well, you can define a space called Y in P, which is basically those supersymmetries which are square zero. This is sometimes also called the nilpotent variety of the pure spinor space, or the Maurer-Cartan space of your Lie algebra P. And this equation here, lambda alpha gamma alpha beta mu lambda beta equal to 0 is basically the first, like that's the original equation for pure spinors that was used. Some more about pure spinors. So we have our space Y here, and this equation then lambda gamma lambda defines an ideal inside the polynomial ring generated by the lambdas, and then we can define the ring of regular functions on Y as just the quotient of it. So this is basically then functions on the space of pure spinors. In the literature, this is sometimes also referred to as the structure sheaf. Don't really ask me what a sheaf is, but that's what it's called. So how does the pure spinor construction work? Well, to avoid using too fancy words, it is a functor. Sorry, Julian, I know you don't like these things, but that's what it is. That takes as input what's called a G0 equivariant module M of OY. So something that OY acts on, and it outputs a P module or a supermultiplet. So for example, we can, as a module, we can use to plug in OY because this thing acts on itself, and this is what's called a canonical multiplet. That thing takes the form of 28, and just some like intuition here. The x here is thought of as coordinates on T2, and theta are coordinates on T1, and this C x theta is then supposed to be thought of as functions on superspace, physically, and so things inside a bullet of a y are what's called pure spinor superfields. So it's something that is dependent on x, theta, and lambda. And then I have some differential. Importantly, supersymmetry here is now strictly satisfied. So P acts through these vector fields that I've written down here. You can quite naturally twist the canonical multiplet. So by fixing some q in y, you can define the PQ module a bullet over YQ by basically just deforming the original differential we had by the action of Q. So not only do we deform the differential on a bullet over Y, you also deform the supersymmetry algebra, so then it now becomes a differential graded algebra with a differential which is just the adjoint action of Q. So the idea of this big construction is that this D here in 28 is supposed basically to serve as the this whole thing is supposed to model some BV multiplet of your supersymmetry algebra. Of course, this is the D here is not the BV differential that you would normally see, but by going to a smaller model, there's a procedure for obtaining, for example, a BV multiplet with your ordinary component fields. So important examples of the canonical multiplet is, as I've said earlier, D equals 10 superYoung-Mills and D equals 11 supergravity. And so basically what this means is that you can find, if you have the, one thing you can basically, by starting with the canonical multiplet, move to a smaller multiplet by this procedure I mentioned earlier of the homological perturbation lemma and homotopy transfer to basically end up at the ordinary multiplet for 10-dimensional superYoung-Mills or 11-dimensional supergravity. Now, importantly for us, the canonical multiplet is also a commutative algebra. And in fact, this structure is important in several examples, and in particular in 10-dimensional superYoung-Mills and 11-dimensional supergravity, it corresponds even to the the interactions of the theory. In some sense, we might be, I should say, it's the color stripped interactions of the underlying field theory. So the formalism not only produces a supersymmetric multiplet, but it actually allows you to, in some examples, construct the full interacting theory. So instead of just getting something which on which P the supersymmetry just acts, you get your interactions as well, and that's basically what I'm quite interested in. I noticed that I have to speed up a little bit, but so the canonical multiplet is a module of your supersymmetry, but it's also an algebra, and this is exactly why these open-closed homotopy algebras are important, because what we see is that the action of your supersymmetry is in fact as with respect to as derivations with respect to the multiplication on your canonical multiplet. So the canonical multiplet then is in fact an example of an open-closed homotopy algebra. And by homotopy transfer, this gives rise to an open-closed homotopy algebra on the cohomology. So not only the interactions, but some interplay between the actions of your supersymmetry and the interactions of your theory. So you might ask, but then the physical interpretation for these this open-closed homotopy algebra structure is. So if you recall that the open-closed had things which takes things in your supersymmetry algebra and takes things in your takes in fields and then gives you back fields. And so the notion of an infinity or a homotopy representation oftentimes it explains the appearance of what's called linearized on-shell symmetries in physics. And it's natural that these higher things, the higher maps in the open-closed homotopy algebra would compensate for the fact that symmetry algebra closes modulo the full interacting equations of motion. This would be a very interesting small exercise to actually compute these. I haven't done that, unfortunately, but it would be nice to do that in some examples. Finally, this is not exclusive to the canonical multiplet, so you can find other multiplets which in principle would be an example of an open-closed homotopy algebra. Right. So the canonical multiplet is not freely generated as an algebra, and that's basically because OY is just a quotient space. And in my previous paper with Cederwall, Saveri, and Palmquist, we used something called a Tate resolution to resolve. So following the big general philosophy back in the beginning of the talk, we can resolve the canonical multiplet to just a freely generated commutative algebra, and this is some procedure where you try to resolve then OY, and what you end up with is a freely generated commutative differential graded algebra whose cohomology is precisely OY. And if you recall way back in the beginning when I talked about packaging the higher brackets of an L-infinite algebra inside the differential of freely generated commutative differential graded algebra, this Tate resolution is in fact then Koszul dual to some L-infinite algebra, which we call T tilde here. Which is why I have this suggestive notation C below of T tilde in 31. So C below T tilde is the resolution of OY. And then in this paper, we then developed a span of infinite algebras, which are a commutative algebra is an example of an infinity algebra. So in particular, we have the canonical multiplet here on the left, and then we can actually plug in the Tate resolution inside the pure spinor functor. And then C below of n here is some subalgebra of this L-infinite algebra T tilde. Basically what my questions were when writing my paper were, okay, how does this span behave under twisting? And can this span be extended to one of open-closed homotopy algebras? So I basically asked, okay, how does these map then work in these settings? And so very quickly, you can right. I'm going to do this a little quickly. So we're going to start with the left-hand side of this span. So in the old paper, we defined an equivalence between tilde a bullet and a bullet of OY. And this is done through a procedure of just using the HPLs several times. And the only difference here is that we also now have this twist of Q. So you can define some homotopy deformation retract from the twist of a bullet of Q to the twist of the canonical multiplet. And then just like the okay, and here is a perhaps a tricky thing, so I'm going to try to do it slowly. So as we saw before, the canonical multiplet is an example of an open-closed homotopy algebra. This tilde a bullet, which is then the multiplet corresponding to putting in what's called the Tate resolution of OY. So this C bullet of T tilde also carries an open-closed homotopy algebra structure. And so we can and so by some previous algebra, we have a different deformation retract of DG vector spaces here, 38, from a bullet tilde Q to the canonical multiplet. And if you recall from earlier, we can use homotopy transfer to induce an open-closed homotopy algebra structure on the canonical multiplet. But there is already an open-closed homotopy algebra on the canonical multiplet. So then the question is, are these two the same? This is essentially just a bookkeeping exercise to actually compute the homotopy transfer and just validate that it is in fact the same. Once we've done that, we end up with this proposition which says that they are quasi-isomorphic as open-closed homotopy algebras. And then we can move over to the right-hand side of this span, and it's a very similar exercise. So you can we know from before that the non-twisted things are quasi-isomorphic, and in fact we can find a deformation retract between these. And then what we do is then we deform the differential on the left by adding this twist, and then running the HPL to see what kind of differential we end up with on the right-hand side here. Interestingly, since C bullet of n is well, and this will then give us a new differential on C bullet of n, and recall the previous again the previous thing about causality of having a L-infinity algebra be equivalent to freely generated commutative differential gradient algebras. We get a new L-infinity algebra structure on n, and their bracket can be written as in 41 here, which is basically just the new maps are you fill in you feed in Q in some spaces, and you feed in your input in some spaces. And this is in fact the L infinity version of twisting like the twist of an ordinary Lie algebra by a Markov-Hahn element. So this 41 here is in principle then the L infinity version of this. And
so there is a question from chat. If you can.
Yes, sorry.
I missed that.
Chat. Okay, very good. So, sorry. N is. Thank you, Jimmy. I didn't go through this in very much detail, but N is basically computed by doing this Tate resolution. So if we go into a little bit more detail, the Tate resolution is basically you start with OY, and then you introduce extra extra generators to produce the cohomology that you want. But by doing so, you might create more cohomology, and so you have to introduce more generators to kill that cohomology, and so on and so forth. And basically these higher generators form corresponds to N here. Okay, this is basically this is my last slide. So let's just say this briefly, and then I'm happy to answer more questions. So this is the main result is then that the answers to the previous two questions is yes, in the sense that we have a quasi-isomorphism of open closed or homotopy algebras, or what's called also A infinity algebras over the strict L infinity algebra PQ. Right, I think I'm gonna stop there.
Okay, thank you very much for our talk. It's very concise and interesting, I guess, for all of us. So it might spark a few questions. So please.
So maybe I can ask. So can you hear me?
Yeah, I can hear you.
Okay, good. Yeah, thanks for the talk. Very nice talk. So can you say in some very concrete examples what the canonical supermultiplets give in in 11D? Like you get the gravity supermultiplet, or
what the canonical multiplet corresponds to?
Mm-hmm.
Yeah. So were you to for example, yes, if you choose as your supersymmetry algebra your like any 11-dimensional supersymmetry algebra,
Mm-hmm.
and you plug in and you do this procedure and you get the canonical multiplet for that, then you can do a procedure where you basically move from this huge model which with like a bunch of fields
Mm-hmm.
to a smaller one, and that model is exactly the BB multiplet for
Mm-hmm.
supergravity. I think there are some see like you have the ordinary like Gravitino and Yeah, I've forgotten what the multiplet looks like, but
but you recover the stuff that, you know, like the fields in that appear in 11D Sugra, right? Like
yeah,
like
you recover the stuff.
I see. And is this in every dimension? Do you recover kind of the minimal, or I don't know how to call it, supermultiplet? If you take the algebra to be like the supersymmetry algebra in the given dimension with some amount of supersymmetry.
Yeah. So if you, I think, well, you mean if I take as my supersymmetry algebra like a minimal, like with minimal supersymmetry?
Yeah. Let's say yeah.
Yeah, I think. I mean, so the examples which I know the best is 10D supermultiplets and 11-dimensional supergravity. But yeah, if you so in 10 dimension, if you choose the minimal one, you get a model which is quasi-isomorphic to the BV multiplet for 10-dimensional supermultiplets as the.
Oh, I see. So you don't get gravity in 10 dimensions from this.
Well, good question. So I think you can, because this procedure is exhaustive in the way that in the sense that you can produce any supermultiplet. So the question is then just, it's not necessarily the case that it's the canonical multiplet.
Right.
The thing that you want.
So
you need to find the right thing to put into your functor, right?
I see. But you say that the canonical one in 10D is not the gravity one, but the one with gauge fields, like the
Yes.
Interesting. Okay, I see. Thanks. Cool. Thanks.
Could you please enlarge your presentation?
Of course.
I struggle to enlarge it a bit more. Yeah, thanks.
Yeah, sorry. Can you hear me?
I can hear you. Yes.
Thank you for the talk. I wanted to ask. So how should I read this result, the main result, the span? Should I read this in terms of like, is so maybe first question is so I imagine that these are now like three equivalent structures in the span, since they're isomorphisms. And if that's the case, should I read it as should I read this as a recipe to understand the left hand side, the twisted supermultiplet, in terms of these generators from the date resolution? Is this does this simplify the description of the twisted supermultiplet? Or
Okay, thank you. Very good question. Let's see if I can I can answer. But so in principle, yes. As I mentioned earlier, the canonical multiplet as an algebra is not freely generated, because we have this this quotient, and so we one question you can ask is, okay, well, can we find some model which is like even more nicely behaved than the canonical multiplet already is? And that's basically what this Tate resolution does. And the right hand side of the span, so C bullet of n, is in principle a minimal version of like it's a model of the canonical multiplet which is freely generated but minimal. in the sense that it's like small. Another thing that like brought up the reason why we were interested in this, we being like based on the previous paper that I wrote with Cederwall, Palmqvist, and Saberi, was that in broad strokes that Koszul duality is like interesting, and since the canonical multiplet is a commutative algebra, one can ask the question, what is an appropriate notion of its Koszul dual L-infinity algebra? And since it is not freely generated, that question is not direct, like it's not easy to directly answer that, and that's why we had to go to this Tate resolution of finding a model which is freely generated, and then from that find the Koszul dual L-infinity algebra. And that's the role n plays here as the L-infinity algebra Koszul dual to the canonical multiplet. It was a quite long explanation, but hopefully it was okay.
So for thank you. Also for as a general, for case of general open-closed homotopy algebra, would this work the same or similar, or is it is this specific to supermultiplet?
What result is? You mean if I take a? I'm not sure I understand the question. Sorry, could you say it?
Yeah. Sorry, so maybe I'm just wondering what's the so what would be like the most general setting where we could do this, where we could understand an open closed homotopy algebra, in terms of a resolution of this kind.
The most general setting. I'm not sure I'm answering the question now, but like open closed homotopy algebras like are well defined for any, like you don't have to deal with supersymmetry to like define them. So they're more general than only for supersymmetry. Whether there is a whether there's a more general Are you asking if I can like generalize this span further in some sense, or?
Yes, just this. I'm like of course I I'm not exactly sure what I'm asking about. Just yes, in this general direction. Yeah.
Oh, I see. Well, okay. I think I mean, you can of course, well, I mean, yes, you can generalize it. I suspect in the sense that perhaps you can find. So this thing has been, what I've done is exclusive to the canonical supermultiplet. So it's for a very specific one. It's general in the sense that I can choose whichever supersymmetry algebra I want, but it's still only one multiplet for that specific choice of supersymmetry algebra. But I guess you can perhaps try to generalize this thing to the setting where you have any type of supersymmetry multiplet, which also carry an open closed homotopy algebra structure, and try to do this resolution, if that makes sense.
Okay, any other question?
Yeah, thanks a lot.
Thank you.
So maybe I will have one short question coming from my confusion.
I still understand. Thank you very much. It was very nice.
Thank you.
Once you constructed a canonical multiplet,
Yes.
you claimed it can be furnished with open-closed algebraic data.
Yes.
And I'm not sure I understand how can one perturb this this algebra by some charge once we are actually dealing not only with closed or open homotopy algebra, but both. Does the result about homotopy perturbation lemma survive the transition from let's say L infinity or A infinity setting to the generalized setting?
Right. So are you like well versed in homotopy transfer, or right? So there is a open closed homotopy algebras are a sufficiently nice homotopy algebraic structure in the sense that homotopy transfer is possible. So just like you can transfer L infinity algebra structures like ordinary, you can transfer like the full compact open closed homotopy algebra structure.
Okay.
If,
some underlying homotopy theory of the algebras and A infinity algebras might differ, I guess. So it's the only thing I'm a bit concerned with. But yeah, I guess.
Do you mean to ask if I transfer open closed homotopy algebraic structure, is that the same as transferring like
if these formulas you explained to us change somehow, or is it in principle the same story?
It's in principle the same story. That in the sense of like summing over trees, then yes. Yeah, I mean, if you know of this, like the tensor trick, where you like go to the, instead of like transferring, instead of doing homotopy transfer of like L infinite algebras, you do the tensor trick so that you go to the cochains of your corresponding L infinite algebra, and then do the homological perturbation lemma to induce a differential. I think you can in principle do the same thing for an open closed homotopy algebra. So the structure of an open closed homotopy algebra can also be packaged into some freely generated thing with a differential, and then you can like do the homological perturbation lemma in that same sense. And
this is the field of derived geometry I'm not very well acquainted with, so this is my source of confusion. Yeah, but thank you for ensuring me that it works.
Thank you.
Any other question? Yeah, it doesn't seem to be the case. So let's thank the speaker again.
Thank you very much.
Yeah, thanks for your insights and nice answers.
Thank you very much. I enjoyed it. I will try to